Our next topic of discussion is we have to solve for the expression of volumetric strain under triaxial loading. Right? There is a case in which the load is acting on all the three axes and we have to determine what is the volumetric strain in that case. Suppose we have this body, right? We have this member. The length of this member is, let us say, L. L is the length of this member, right? And we are saying B is the width of this member and T is the thickness, or D is the thickness of this member, right? D is the thickness of this member. And I am assuming, this is your x-axis, this is vertical axis is your y-axis, and this is your z-axis. I am taking this x, y and z. Suppose this load or this body is under the load in all the three axes, and we are saying that the load on x-axis will be, the normal load on x-axis will be, let us say, px. The normal load on y-axis will be, let us say, py. And the normal load on z-axis will be, let us say, pz. Right, pz. There are three loads acting on the three perpendicular directions, that is px, py and pz. Now we have to find what is the volumetric in this case, volumetric strain in this case. Now let us say that stress is defined as at a point, we know. So let us take this point as our reference and we will study this point. A small element of this point we will study, right? Let us say this is the case. This point we have to study, and I show the state of stress of this point here. This is the state of stress, or you can say non-hydrostatic state of stress at a given point. That this point, let us say this point is A. At this point A, the state of stress is, because of Px, a normal stress on x-axis, that is sigma x, a normal stress on y-axis, that is sigma y, and a normal stress on z-axis or z-face is sigma z. We have these three different normal stresses value. The magnitude of all these are different, so it is a non-hydrostatic state of stress. We know the hydrostatic state of stress means all the values of sigma will be same and direction will be same. So if I represent the state of stress at this point with the help of a stress tensor, I can say on the x face, this is your x face, on the x face normal stress is sigma x, tau xy is 0, tau xz is 0. On the y face, tau yx is 0, sigma y is sigma y, tau yz is 0. And on this z face, tau zx is 0, tau zy is 0, and sigma z is sigma z. These are the stress tensor for this triaxial loading case, right? And we know from our basic definition of volumetric strain, that is volumetric strain is change of volume upon original volume, and that is equal to strain on x-axis plus strain of y-axis plus strain of z-axis. We know this is a strain. Volumetric strain is equal to strain in y-axis plus strain in x-axis plus strain in z-axis. We know this. Now let us find what is the strain in x-axis, what is the strain in y-axis, and what is the strain in z-axis because of this triaxial loading case, right? Now this is the case when all the three loading, that is px, py and pz, are acting simultaneously, right? We have the relation of stress and strain for the uniaxial case, right? We know that normal stress upon longitudinal strain is Young's modulus of elasticity under uniaxial state of stress. So we are assuming, we are dealing with this equation like this. We are assuming that suppose only Px is acting alone. Only Px is acting. So what are the various strains? Second is when only Py is acting, these are zero. Only Py is acting, so what are the strains? And when Pz is acting alone, what are the strains? And we can combine all this to find what are the total strain in this member. So first one, I am treating that, let us say that only Px is acting, right? So this is the case that if suppose this is the member, this is our member, this is the longitudinal axis. The first case is when your Px is acting alone. Only Px is acting, and that is along the length, that is along this length L, right? That is along this length L. We can say that because of this Px is acting, because of this Px, this sigma x is there, which is equal to force Px upon your area of cross section, right? And area of this cross section is your B into D, but I am writing only area. Area will define later on. Sigma x is equal to Px upon A. Now we know that this is the case of, if I write, this is the case of uniaxial loading, right? This is the case of uniaxial loading, and for uniaxial loading we know that normal stress upon longitudinal strain will be equal to Young's modulus of elasticity. We know this. So we are saying that in this case the direction of load is x, so the longitudinal strain will be epsilon x, right? In the direction of load the strain will be epsilon x, or we can say the longitudinal strain will be along the direction of load, that is epsilon x here. So I can write that epsilon x, which is a longitudinal strain in this case, the value of this will be sigma x upon E. Sigma x upon E. And this is positive because this is a tensile load. So the longitudinal strain which is along the x-axis will be equal to sigma x upon E. Now we say that, we already see that for a longitudinal strain, the longitudinal strain is associated with two lateral strains in the other two perpendicular planes and of opposite nature, right? This we know that if any longitudinal strain is there and one longitudinal strain is associated with two lateral strains in the perpendicular planes and of opposite nature. So I can say that if Ex is a tensile strain, then because of Px there is a strain in y plane, that is a lateral strain, and that will be equal to minus mu times epsilon x, minus mu times epsilon x. Why? Because we know that the Poisson ratio will be lateral strain upon longitudinal strain. Lateral strain upon longitudinal strain. So from here you can say lateral strain will be equal to Poisson ratio into longitudinal strain. So and of opposite nature, so this is minus, because this is positive, this is your tensile. So the lateral strain will be your compressive nature, and that is equal to minus mu times epsilon x, or epsilon longitude, that is sigma x upon E. And similarly your epsilon z is also a lateral strain in the z direction because of load Px. Because of Px, in x direction it is longitudinal, in y and z direction it is lateral, and as this is negative, this is positive, longitudinal is positive, so lateral will be negative, and that is minus mu times sigma x upon E. This is also a compressive strain. Right, this is also a compressive strain. So these three strains are acting when Px is acting alone. The second case is when your Py is acting alone. This is the case when your Py is acting alone. So I can say that only in this case only Py is acting like this. Py is acting. If Py is acting alone, so we can say that sigma y will be equal to Py upon area. Just remember that if you want to find sigma x, that is Px into area of this plane, sigma y will be Py into area of this plane. Right? Area will be depend upon the plane. So sigma y will be equal to Py upon area. So this Py is a normal load. Because of normal load, normal strain will occur, and in the y direction, this load is in the y direction, so I can say that the strain in y direction will be equal to your longitudinal. In this case it is longitudinal because the load is in y direction, and longitudinal strain is equal to your stress sigma y upon E. Sigma y upon E, because this is a uniaxial state. This is also a uniaxial state. Just remember one thing, you cannot write these formula that strain is equal to stress upon Young's modulus for this combined loading. This is not valid. It is only valid for uniaxial state of stress. So I am taking the when Py is acting alone, when Px is acting alone. So if there is a longitudinal strain in the y direction, so because of longitudinal strain there are lateral strain on your x and z direction, and lateral strain will be of opposite nature. This is your tensile. I can say this is the tensile. So the lateral strain will be compressive. So this is minus mu times sigma y upon E. And similarly in z direction the strain will be lateral, that will be equal to minus mu times sigma y upon E. Both of them are of compressive nature, opposite to the nature of longitudinal strain. The third one is when your Pz is acting alone. Suppose this is the case, this is the member. When your Pz is acting alone in this plane, this is Pz. Pz is acting alone, so this is also a kind of uniaxial state. So in this case, the normal strain in the z direction will be your longitudinal, because the direction is in z direction, that will be equal to sigma z upon E. And what is sigma z? Sigma z will be equal to Pz upon area of this front cross section, right? Area of this front, Pz upon A. If z in z direction it is longitudinal, so in x direction it is lateral. In x direction it is lateral, that is equal to minus of mu times sigma z upon E. This is positive, so this will be negative. So epsilon y is also lateral, so this is E lateral, that is also equal to minus mu times sigma z upon E. Sigma z upon E. So there are total 9 strains are acting, out of which you can say 3 are longitudinal. If I circle, 3 are your longitudinal, these 3 are longitudinal, and other 6 are lateral strains. So if I draw a table here, that this in this vertical columns we are fitting stress and this is strain. So I am writing, just please pay attention here. For the stress sigma x, if sigma x is acting alone, then in the x direction the strain will be sigma x upon E, and in y direction the strain will be minus mu times sigma x upon E, and in z direction also this is minus mu times sigma x upon E. This is when Px is acting. When your only y is acting, so in the y direction it is longitudinal, that is sigma y upon E, and in both other x and z it is minus mu times sigma y upon E. This is minus mu times sigma y upon E. When sigma z is acting alone, Pz is acting alone, in the z direction the strain will be the longitudinal, that is sigma z upon E, but in x and y it is lateral sigma z upon E minus mu times sigma z upon E. These are the three strains acting on these are the 9 strains acting on this triaxial loading case. Now if I want to know what is the total strain in x direction, the total strain in x direction will be the summation of all these three. The total strain in y direction will be the summation of these three. The total strain in z direction will be the summation of these three. So if I write that what is the total strain, epsilon x is strain in x direction, strain in or normal strain in x direction, that is equal to change of length upon original length, and this is equal to the summation of this, that is your sigma x upon E minus mu times sigma y upon E minus mu times sigma z upon E. This is the total strain in x direction. Total strain in x direction, or I can write this, I can solve this further here only. So I can write this equation as, just to remember, this will be 1 upon E into sigma x minus mu times sigma y plus sigma z. This is the total strain in x direction. The total strain in y direction is the summation of all these three, and the y direction dimension is b. So the total strain in y direction will be change of width or depth upon b, delta b upon b. This will be equal to summation of this, that is your, if I write directly, this is 1 upon E into sigma y minus mu times sigma x plus sigma z. You have to learn these results to use directly in your GATE exam. Epsilon z is the total normal strain in z direction, that is the summation of all these three, and in z direction the dimension is your d. So the epsilon z will be equal to delta d upon d, which is equal to 1 upon E into sigma z minus mu times sigma x plus sigma y. Sigma x plus sigma y. Just remember, if here it is z, then sigma z minus mu times the rest 2. Sigma y, this is sigma y minus mu times rest 2. Or epsilon x is equal to sigma x minus mu times sigma y plus sigma z upon E. This is the formula for these formulas are giving you the normal strain in the mutually perpendicular direction under any state of stress. Any state of stress condition, these three formulas will give you the normal strain in these three perpendicular directions, that is epsilon x, epsilon y and epsilon z. And we know that the summation of epsilon x plus epsilon y plus epsilon z, epsilon x plus epsilon y plus epsilon z will be equal to volumetric strain. It will be equal to volumetric strain, right? Volumetric strain is your summation of all these. So if you solve for this, then the volumetric strain will be equal to, if you add all this, then the volumetric strain will be equal to 1 minus 2 mu into, or divided by E into sigma x plus sigma y plus sigma z. This is the expression for volumetric strain under triaxial loading. Under triaxial loading, this is the expression for volumetric strain, that is 1 minus 2 mu upon E into sigma x plus sigma y plus sigma z. This you have to learn. This formula you have to learn, and these are the strains in all the three directions, and this is the total volumetric strain, that is 1 minus 2 mu into sigma x plus sigma y plus sigma z upon E. So this is the expression for volumetric strain under triaxial loading.